Welcome to Pastor Victor's Academy. Embark on a journey through the world of engineering mathematics and electrical engineering with our educational tutorials designed specifically for engineering students. Whether you're mastering calculus, solving complex circuit problems, or exploring power systems, Pastor Victor's Academy is your ultimate learning companion. Join us as we break down complex concepts into clear, easy-to-understand lessons, helping you build the foundational knowledge and skills needed to excel in engineering mathematics and electrical engineering courses. Subscribe now to kickstart your learning journey and gain the confidence to tackle engineering challenges head-on. Let's unlock the world of mathematics and electrical engineering together, one lesson at a time.
Good day. Welcome to Pastor Victor's Academy. It's nice having you here again. The other time we talked about functions. So today I want to talk about finding the domain and range of a function. Remember we said a function is an expression that describes the relationship between a variable which is known as the output variable and another variable which is known as the input variable. Now, here is a function y defined in terms of x. So you'll have y equal to 2 over x. This is a function. Now the question is, why are we interested in knowing the domain and range of a function? And why we're interested in knowing the domain and range of a function is because not all values can be the input value of a function. Not all values can be the output value of a function. There are times that certain values are excluded. So in that case, we want to know what is the domain of a function about and what is the range of a function about. So the domain of a function is a set of all possible input values. Take note of the word possible. There is a value that cannot be an input value. The same thing happens with the range. The range is a set of all possible output values, meaning that there are values that cannot be output values of a function. Now, using this function, for example, we'll have the number line. We are moving from negative infinity to positive infinity. And here we can have -3, -2, -1, 1, 2, 3. Now, as we begin to move from negative infinity to positive infinity, we realize that the moment we get to 0, this function becomes undefined. We'll be having y equal to 2 over 0. If you use your calculator, you punch this, it will give you error or expression to show that this has no definition. Now, meaning that any value on the number line can be an input value for this function except 0. Except 0. Every other value can be an input value. Only 0 is excluded from the domain. Now, let's talk about the range. We still have 2 over x. So we want to know what are the values that this function would generate. Is there a particular value that this function will not generate? Yes, there's a particular value. Now, that value is 0 also. Let's do this. 2 over x equal to 0. What do we have? Making x the subject, we have that x is equal to 2 over 0. What does this mean? That for you to have 0 as the output value, x must be 2 over 0. And we can never have this as an input value. We cannot have this as an input value. So in that case, we shouldn't expect 0 as an output value. So the domain of this function includes all values except 0. Whereas the range of the function includes all values except 0. We'll be having negative infinity comma 0 union 0 comma infinity. You can also express it this way: negative infinity less than x less than 0 and 0 less than x less than positive infinity. The range will now be minus infinity. This is still the range, but in case we want to express it using inequality, we would say minus infinity. So if we want to express it using inequality signs, we can put it this way: minus infinity less than y less than 0, and 0 less than y less than infinity. So this expression excludes 0 and excludes negative infinity and positive infinity. Let's take another example. I'll draw the number line again. We have positive infinity, negative infinity. Let's say we have y equal to 2x plus 5, y equal to 2x plus 5. We want to know, as we move towards positive infinity, is there a particular number that cannot be an input value for this? Let's check. Put 1, put 2, put 3, put 4, put 0, put minus 1. Keep going down towards negative infinity. You will discover that there is no value that this function cannot take as an input value. And when you begin to check for the range, you also realize that there is no value that this function cannot generate. So in that case, both the domain and range are negative infinity to positive infinity. So if you want to express it using inequality, we just say minus infinity less than x less than infinity. Minus infinity less than y less than infinity. So that's what domain and range is about. We want to know the values that can be the input value of the function and the values that can be the output values of a function. Before we go into the main thing, we want to talk about handling boundary values. Because when talking about domain and range, definitely you need values that will be your boundary values. Take for instance, I'm using these guys here as boundary values. The other example I gave, 0 was part of the boundary value. Now, how do we show that boundary values are either included or excluded from the domain or range? That's the next thing I want to talk about. So let's assume we have a number 2. Then we have the boundary value and we have this. So this a number, a finite number, whereas this is an infinite number, or in other words, negative infinity. So what this means is going towards the negative direction without limits. Whereas this one means going towards the positive direction without limits. So you can pick any number in the positive direction. You can pick any number in the negative direction. Whereas this one is a specific number 2. Now let's assume that 2 is not part of our domain. Let's assume that 2 is not part of our domain. How do we express it? Now, using brackets, we have the normal brackets, we have the square brackets. We would say negative infinity, comma, 2. Now, union 2, comma, infinity. So we had to split it into 2 because that's the only possible way to show that 2 is not part of the domain. You will see that I used brackets. That's normal bracket here, here, and here. So whenever I'm using normal bracket, it shows that the value, that's the value that is at that boundary, is not part of the domain. But when I use a square bracket, take for instance 2 is part of the domain, and let's say another number 3 is a boundary value and part of the domain. I can say negative infinity, comma 2, then union 3, comma infinity. So what I'm saying in essence is that when a value is not part of the domain or range, we use a normal bracket. But when a value is part of the domain or range, we use a square bracket. Now, using inequality to show it, this guy is the same thing as less than or equal to. Whereas this guy is the same thing as greater than. Then this guy is the same thing as greater than or equal to. Whereas this guy is the same thing as what? Less than. So you may want to know about this guy and this guy. This is negative infinity, whereas this is positive infinity. We don't know the limits. As we begin to move towards the negative direction, we don't know the limits. As we begin to move towards the positive direction, we don't know the limits. So in that case, we can't use a square bracket. Neither can we use greater than or equal to or less than or equal to. Instead, we use normal brackets, greater than or less than, to show that they are boundary values. So that's that for boundary values. So how do we find the domain of a function? How do we find the range of a function? I believe you are interested in knowing how to find the domain or range of a function. Except the domain of a function is defined, finding the domain of a function requires knowing the values that make the function undefined and using those values as the boundary values. So in order to find the domain of a function, the first thing we look out for, what are the values that make the function undefined? So when we're able to identify these values, we can now use those values as boundary values. There are common undefined conditions in mathematics, so I'll be listing them out. The first one is A over 0. A over 0. So anytime you find this condition, it is undefined because we can't have 0 as the denominator. That's the first one. The second one, root negative A. Now, A here is a number. 1, 2, 3, 4, 5. The root of a negative number is undefined. So we don't know what it is. It's undefined. Now, before we go ahead, I want to say this. Functions can be combined under the action of the arithmetic operators as long as they have a common domain and the new function remains valid within the common domain. What does this mean? You can add two functions, you can do subtraction, division, multiplication, as long as the two functions have a common domain and the result you will get will be valid within that common domain. So let's take examples. Find the domain of the following. I, y equal to 5x plus 3, y equal to 2x squared plus 1, I, y equal to 1 over 7 minus x, and iv, y equal to 4 over root x plus 1. Now, how do I find the domain? I've already said that. The first step is to look out for undefined conditions. So for the first one, y equal to 5x plus 3. We cannot have an undefined condition here. Any value you put here will give you an answer. So the domain becomes negative infinity to, sorry, comma, positive infinity. Or we say x less than infinity but greater than negative infinity. So this implies that this function can take any value as the input value. So that's for that. The second one, y equal to 2x squared plus 1. The same thing applies to this. Any value you put here will give you a result. So it can take any value. In that case, we'll have negative infinity, comma, positive infinity. Now the third one, we'll have y equal to 1 over 7 minus x. We have a condition that will make this function undefined. And that condition is when the denominator is equal to 0. So what do? We equate the denominator to 0. Any value that satisfies that condition is the excluded value. So we go ahead, 7 minus x equal to 0, x is equal to 7. So it means that x can be any value but not 7. X can be any value but not 7. So in that case, we'll be having minus infinity, comma, 7 union 7, comma, infinity. So this becomes our domain for this function. You can write it this way. Minus infinity less than x less than 7 and 7 less than x less than infinity. Okay, let's solve the last one. Now there are two conditions that will make this function to be undefined. The first one is that the denominator must not be 0, and the second one, that's root x plus 1 should not be equal to 0, and the second one, root of a negative number. So that means root x plus 1 must not be less than 0. So these are the two conditions that will make this function to be undefined. The moment x plus 1 is equal to 0, the function becomes undefined. And the moment root x plus 1 is less than 0, the function also becomes undefined. So we will use these conditions to find out the value we are looking for. So combining these two conditions, we can say root x plus 1 less than or equal to 0. So that means root x plus 1 must not be less than or equal to 0. So in that case, we'll be having x plus 1 less than or equal to 0, x less than or equal to minus 1. So once x is less than minus 1 or equal to minus 1, this equation becomes undefined. So it means that for the domain, x is greater than minus 1. That means we'll be having minus 1, comma, infinity. So here is the domain for this function. We can also use inequality to express it. That means we'll have minus 1 less than x less than infinity. So the domain lies within here. It is not equal to minus 1. It is not equal to infinity. It's within this boundary. How do you find the range of a function? The range of a function is found by knowing the values that cannot be the result of a function for each valid input and using those results as the boundary values for the range. So we're almost doing the same thing we did for the domain, but in a different way. So how do we go about it? Find the range of the following. So the first method is the graphical method. How do you do it? Plot the graph of each function. Now you look at the vertical axis. Anywhere there is a gap on the vertical axis, that place is excluded. That means it's undefined. So any value there is an excluded value. The second method is making x the subject of the formula. So for each equation here, we'll make x the subject of the formula. We'll now find the values that make x to be undefined. So those values become boundary values for the range. And the last one is using limits, the concept of limits. But we'll focus on the second one and also see how to apply the last one. How do we find the range of these equations? The first one, y equal to 5x plus 3. Make x the subject of the formula because we cannot be plotting graph with this. You can use your graph plot on your phone and you do that, you'll be able to find where you have an asymptote or a gap on the vertical axis. So we are using equation. What do you do? Make x the subject of the formula. We have y minus 3 equal to 5x. X is equal to y minus 3 over 5. Since the denominator is not 0, it's a constant, it means that all the values you put in here will give you an output. So there is no excluded value. In that case, the range is negative infinity, comma, infinity. So y can take any value. That's what it means, which you can express using inequality. Let's take the second one. Y equal to 2x squared plus 1. Let's make x the subject of the formula. We'll be having y minus 1 equal to 2x squared, meaning that x squared is equal to y minus 1 over 2, implying that x is equal to root y minus 1 over root 2. So what makes this function to be undefined? What condition makes this function to be undefined? When the root of y minus 1 is less than 0. When the root of y minus 1 is less than 0. So let's see, square both sides, we'll be having y minus 1 less than 0, y is less than 1. So it means that whenever y is less than 1, this equation becomes undefined. So in that case, y cannot be less than 1. So there's no other condition. There's no other condition. Y can be 1, but not less than 1, meaning that y is greater than or equal to 1. So you can see that any number we put here from 1 above will give us uh, an output. So we can express it like this. When you put 1 here, you get 0. Root 0 is 0. So we can express it like this: 1 comma infinity. Any number less than 1 is excluded from the range. Let's solve the third one. Let's make x the subject in the third one. We are having y into 7 minus x equal to 1. 7y minus xy equal to 1. 7y minus 1 equal to xy. X is equal to 7y minus 1 over y. So what condition makes this equation to be undefined, as this function to be undefined? When y is equal to 0. That means y can be any number except 0. So in that case, y is not equal to 0. Another way of expressing it is by saying negative infinity comma 0 union 0 comma infinity. So any number can be the range except 0. Now the last one, we have y equal to 4 over with x plus 1. Making x the subject of the formula, have y squared into x plus 1 equal to 16. Then we'll be having y squared x plus y squared equal to 16. We're having x equal to 16 minus y squared over y squared. Now, the only condition that makes this equation undefined is when y is equal to 0. So when y is equal to 0, this equation becomes undefined. So in that case, 0 becomes our excluded value. Now let's write the range. The range becomes negative infinity comma 0 comma union 0 comma infinity. Before we go ahead, it's necessary to verify something, because looking at this, we may assume that this is the range, but the truth is that this part is also excluded from the range. The only values that are part of the range are between 0 and infinity, whereas 0 is not included but an excluded value. It's just here as a boundary value. Let's verify. To have y equal to 4 over root x plus 1. Remember that the domain of this function is equal to x greater than minus 1, implying that x cannot be equal to minus 1, else the denominator will be 0, and x cannot be less than minus 1, else the denominator will be negative. So if we begin to pick values between minus 1 and 0, let's see what happens. Because we cannot pick minus 1, neither can we pick a value below minus 1. Let's pick minus 0.9 and 0. Y equal to 4 over root 1 minus 0.9, which is equal to 4 over root 0.1. So you can see that this will give us a positive value. Let's also pick 0. Y is equal to 4 over root 0 plus 1, which is equal to 4 over root 1, which is equal to 4, which is also a positive number. So as we keep going on from minus 1 towards positive infinity, we will definitely get to positive number. When x becomes a positive number, definitely this function cannot be negative. So which means that this guy is not part of the range, because we cannot get a negative number for this function. We can't get a negative number for this function. So we can only have positive number. Therefore, the true range is 0 comma infinity. So we can put it this way: y less than infinity greater than 0. So 0 is not part of the range, it's just a boundary value. Infinity is not also part of the range, it's just a boundary value. In case you are still confused about converting this to inequality, here, remember I told you this means greater than, this means less than. Then if you put y here, it means that y is greater than 0, y is less than infinity. Combining these two expressions, because this we have the same y, is greater than 0 and less than infinity. So we have it that y is less than infinity, then y is greater than 0. Or 0 is less than y, then y is less than infinity. I want us to verify the same answer using the method of the limits. Now, we have 4 over with x plus 1. Then we have the domain to be minus 1 comma infinity. So we'll be checking what the limit will be as x tends to minus 1 and as x tends to infinity, because these are our boundary values. So as x tends to the boundary values, we want to know what y will be. Let's take the limit of the function. We have limit of 4 over root x plus 1 as x tends to negative infinity. Now, because this other part is excluded, we'll be moving from the right. So we'll be having plus sign to show that we are moving from the right. That means on the number line we have minus 1, then we have infinity here. So we tend towards infinity and we tend towards 0. So here is called a positive approach. Now let's see what happens as we move towards minus 1 from the right. The numbers we have when moving from the right, we have minus 0.999 minus 0.99 and minus 0.9. So you can see that we are very close to 1, but we are not at 1. Let's see what happens to this function. We will have 4 over root 1 minus 0.999, which will be giving us 4 over root 0.001. So let's take note of this answer. Then for this one, we'll be getting 4 over root 0.01. And for the other one, 4 over root 0.1. So you can see that this is smaller than this, and this is smaller than this. So in that case, this guy is greater than this, and this guy is greater than this. That means as we move towards infinity, the value tends towards 0. Then as we move towards minus 1 from the right, the value becomes bigger and tends towards infinity. So in that case, we'll be having infinity as our answer. That's positive infinity as our answer. Now, taking limits of 4 over root x plus 1 as x approaches infinity. Already I've said that it gives you 0. In order to verify, we say 4 over x squared over root 1 plus 1 over x. So substituting for x using infinity, we're having 4 over infinity squared over 1 plus 1 over infinity. Take the roots. So this will be giving us 0. This will be giving us 0. We have 1 here. So we have 0 over 1, which is equal to 0. So you can see that we have 0 and infinity as boundary values, no other value. So tending towards infinity, we have 0. Tending towards negative 1 from this side, we have infinity. So in that case, the range is 0, infinity. The negative part is not included in the range. The last thing I want to talk about in this lesson is how to use limits, the concept of limits to find your range. Let's use this one as an example. Y is equal to 1 over y, 7 minus x. Now, we have to get the domain. We will now use the domain with the concepts, alongside the concept of limit, to find the range. So the domain of this function is already we said is equal to negative infinity, comma 7 union 7 comma infinity. So this is what we'll be using, like in this form. So we'll be taking limits as we tend to boundary values. Now let's write out the limits. Limit of 1 over 7 minus x as x tends to negative infinity. That's the first guy. Limit of 1 over 7 minus x as x tends to 7 from the negative side. Then this is our number line 0, negative infinity, 7, positive infinity. So this is the positive side. That's when we are coming like this, when we are going like this, when we are coming like this, when we are going like this. So x tending to infinity, this guy is x, that's this number line. X tending to negative infinity is towards this side. Then x tending to, because this is our boundary, sorry, this is our boundary. So x tending to 7 is this side, negative, from the negative side. Then x tending from this side, x tending towards infinity. So the next one is limit 1 over 7 minus x as x tends to 7 from the positive side. And the last one, limit of 1 over 7 minus x as x tends to infinity. So how do we know the limits? As x tends to negative infinity, that means we'll be having 1 over 7 minus infinity, which is equal to 1 over 7 plus infinity. Then this will still give us infinity, which is equal to 0. Note, any number, let's say c over infinity is equal to 0. As positive or negative infinity is equal to 0. That means the number tends to 0. So in that case, we will say that the number is equal to 0. Now, the next guy, as we move towards 7 from this side, so we have a number like 6.9. We have another number like 6.8. Then let's fix those values and see what happens. Now, if we say 1 over 7 minus 6.8, because you get to 6.8 before getting to 6.9, you'll be having 1 over 0.2, which is equal to. Then you'll be having the next guy, 1 over 7 minus 6.9, which is equal to 1 over 0.1. Now, what do you notice? This number will be bigger than this number because the denominator of this guy is bigger than the denominator of this guy. So this should give us 10, whereas this should give us 5. So you see that as we are approaching 7, the number is increasing. If we take another number, let's say 1 over 7 minus 6.99, we'll be having 1 over 0.01. Yeah, then we'll be having 100. So you can see that as we approach 7, the number is increasing. Increasing. The closer you go, the number is what? Increasing. So in that case, this tends to infinity. So the limit is what? Positive infinity. Already we said that the limit of this one is 0. Now, let's see what happens as we approach from this side. We'll be having 1 over 7 minus. So of course we should have 7.1, 7.2. Okay, let's say 7.01, 7.1, 7.2. So let's use 7.01 first. 7 minus 7.01. So what are we having? We are having 1 over minus 0.1. Then the next guy, 1 over 7 minus 7.1. This should be 0.1. Sorry, this should be 0.1. Then we'll be having 1 over minus 0.1. Then this guy, we're having 1 over 7 minus 7.2, which is 1 over minus 0.2. Now, this guy is equivalent to negative 100. This guy is equivalent to negative 10. And this guy is equivalent to negative 5. So what happens? Here we have minus 100, minus 10, minus what? 5. So what do you see? As we approach 7 from this side, this is minus 5, minus 10, minus 100. That means we are tending towards negative infinity. The number is just increasing, it's not approaching the number. So it's tending towards negative infinity. By the time you are going very close, it's increasing. So in that case, our limit here is negative infinity. Then for this part, we'll be having 1 over 7 minus infinity. And that gives us 1 over negative infinity, which is equal to 0. We can also do it this way: divide numerator and denominator by x. We have 1 over x all over 7 over x minus 1. So by the time you insert infinity, you have 1 over infinity, 7 over infinity minus 1. This is 0 over minus 1. That's 0. So you can see that the limit as we approach infinity is 0. As we approach negative infinity, we have 0. As we approach positive infinity, we have 0. So here is the limit, here is the limit. Now the question is, how do we know if 0, because already we know that this is not part of the domain, sorry, the range rather. How do we know if 0 is part of the range? Because having it as a limit does not imply that it is part of the range. It only shows us that it's a boundary value. So what do? We write out the equation 1 over 7 minus x, equate it to 0. You will see that we'll be having 1 is equal to 0, meaning that there is no value of x. We can't get any value for x that will give us that answer 0. That means since we can't get any value for x that will give us 0, it means that we can never get 0 as an output, because what gives us the output is x. And we are realizing that there's no value for x when y is 0, which means that y cannot be 0. So in that case, 0 is just at the boundary. So y cannot be 0, but y can be very close to 0. So what do we have? We'll be having negative infinity, comma 0, union 0, comma infinity. If you pick another number, let's say 0.1, this is very close to 0. You'll be having 1 equal to 0.7 minus 0.1x. So you can see we have 1 minus 0.7 minus 0.1. So we're having 0.3 equal to minus 0.1x. So x has a value, but in the first case, x does not have a value. So we've been able to get the range of 1 over 7 minus x. Previously, we made x subject, and that gave us the range to be minus infinity, comma 0, union 0, comma infinity, because we realized that y was at the denominator. And if it's at the denominator, y cannot be 0. But from limit, we also got the same result. The only thing is that limit is longer. So we've come to the end of the lesson. Thank you for joining. Please like, comment, share, and subscribe. I hope to see you again in the next lesson. Thank you.